Hello? Can you see where I'm highlighting now?
Yeah.
That is what we call stress field. Okay, so when the magnitude at point stress x alpha is equal to stress x beta, in terms of magnitude is the same, and stress x r at point I and stress x at point j are the same, then we call it symmetrical loading.
All right.
Okay.
Thank you.
Right. So now I'm going to do another example. What I'm going to do is I'm going to bring it back to one because I'm sharing things on two screen. Okay, that's why I think is the part of the reason is crashing. Now if I just use one screen. Okay, so the screen that I write on is what you see. Okay, so see whether will this software crash. Hopefully it does not. If it does, so what you're going to see now is not as comfortable as before, or I need your feedback later, which is better. Okay, right. So the next problem we're going to do is this problem over here. Okay, is this problem we're going to see. Okay, so you guys see a smaller screen now. Okay, so when I write, it moves, the whole thing will shift also. Unfortunately, you don't see the white screen. That's the problem with this method. Right. So this is example number 2. Okay, so two vertical forces applied to the beam. Okay, determine the maximum tensile compression stresses in portion BC. Okay, so we want to look at what is going on between BC. Okay, they specify between BC. Okay, so now we're gonna start this problem. As I said, this problem is a very it's not difficult. Okay, it's not a difficult problem, but you have to construct free body diagram because they don't give you moments at all. Okay, it's just a diagram like this. So now what is our objective? Okay, objective. Now again, I will elaborate that you can get this from Avenue to Learn. Okay, I've put this example on. So we're going to now construct a free body diagram. Okay, and then we are going to look into shear force. Okay, I will do shear force. Okay, and bending moment. Diagrams. Okay. Now you guys have realized that I've not taught very specifically on shear force and bending moment diagrams, but I gave you guys examples already. Why? Because in 2 weeks time, okay, we're going to go in depth mathematically regarding shear force and bending moment diagrams, so you are already seasoned already. Okay, then after that, for this problem, okay, based on the cross sectional area, so if you look at the cross sectional area, right, we cannot find the centroid based on what? Observation. You can't do that. Okay, so we are going to find centroid, which all of you also know how to do already. Okay, so we're going to find the centroid. And second moment of area. Okay, so for this case, the second moment of area will be IZZ. Okay, then we're going to look at stresses. The stresses at specific location. Okay, we'll look at stresses at specific location, and then we are going to sketch. We're going to go for the stress distribution, and the stress distribution is also known as the stress field. They are the same thing. Okay. Okay. So let's do the free body diagram now. Okay. As I said, okay, I will wait for you guys to finish now because I'm on one screen. Okay, so when I move, you see me move. Okay, before that you have a wider screen, and when I move, you don't move. You see, but it keep on crashing my computer, unfortunately. Okay. Right. So we are going to draw our free body diagram. Here we're going to sketch, or we're going to sketch our free body diagram. Okay. So our free body diagram has 150. So I'm going to sketch. So we are going to define a transformation. So this is my. I'm going to go slow. Okay. X, Y, rotation about Z. Okay. And then this is our point A, right? And this is our point D, right? So we have a reaction over here, which is AY, and we have a reaction over here, which is DY. And then we have two loads coming down at point B, and another load coming down at point C. Okay, and both are 10 times 10 to the power 3 Newton. Okay, and then I'll draw an axis at the center. This is known as YY. Okay, so why do I do that? Okay, so based on geometry and loading about the YY axis. Okay, so if we draw a YY axis vertically down, we realize that the left hand side is equal to the right hand side in terms of geometry and in terms of loading, right? So therefore, AY is equal to DY. Okay, so when that's the case, you can do static analysis. Summation of forces in the y direction is equal to 0. So you have AY minus by 10 times 10 to the power 3 minus by 10 times 10 to the power 3 plus by dy is equal to 0. So because AY is equal to dy, so you have 2AY is equal to 20 times 10 to the power 3. AY over here is equal to 10 times 10 to the power 3 Newton, and this is equal to dy. Okay, so you can do that. If you are not sure with this condition, okay, so what you can do, okay, if you are not sure, hey, I'm not sure. You can also, if you don't know this condition, if you're not aware of this condition, fine, no problem. Okay, don't say, oh, we are not taught again, we don't know about this condition. Okay, so I'm teaching you now, but if you don't know, you can still use moment. Okay, so so alternative number 2. All right, alternative number 2. So what we're going to do is we're going to take summation about moment in the z direction at point A. You can do this also. Okay, it's equal to 0, and the answer will be the same. So let me show you. Okay, so what I'll do is I'll get this image so you can see. Okay, you no need to do this. Okay, so you can see when I write. Okay, so that's the problem with using this technique. When I move my screen, you move also, but at least it stops crashing. I hope it stops crashing. It might not. Okay, so we take moment about point A, right? So we have negative 10 times 10 to the power 3 multiplied by the perpendicular distance is equal to 0.15 minus by 10 times 10 to the power 3. Perpendicular distance is what? 0.4. Am I right? Yep. And then plus by dy, and the distance is what? 5.5, 0.55. The whole thing will be equal to 0. Okay, so from here you get your dy. So dy will be equal to 10 times 10 to the power 3, 10 to the power 3, 10 to the power 0.15 plus by 10 to the power 3 times 0.4. So this is 5500 divided by 0.55, right? So this will be equal to 5500 divided by 0.55 is equal to 10 times 10 to the power 3 Newton. Then what you do is you do summation about forces in the y direction is equal to 0 again. So what we will get is ay minus by 10 times 10 to the power 3 minus by 10 times 10 to the power 3 plus by 10 times 10 to the power 3. The whole thing is equal to 0. So from here we can get ay is equal to 10 times 10 to the power 3. Okay. So I want you all to be comfortable. Okay. I don't want you this is based on experience. Okay, if you don't have it, fine. Okay, do it. Okay, you still get the what? You still get the same answer. Okay, just do it. Okay. Now, then from here, okay, we are going to draw. Okay, we are going to draw the shear force diagram. Okay, we are going to construct shear force diagram. Okay, we're going to construct shear force diagram. So the shear force diagram it looks like this. Okay, so the shear force diagram okay, so this is 10. This is minus 10. Okay, and this is V. Okay, so this is 0. Then this is 0.15. This is equal to 0.15 plus 0.25 is 0.4. And then finally, this is equal to, sorry, I'm stumbling down here. The entire length is 0.55. Okay, so this is X. So our shear force diagram at point A, okay, you have 10 kilonewton. So you go up, right? You go horizontal, and at 0.15, okay, at 0.15, let's see over here. At 0.15, you have 10 coming down, okay? So you have 10 coming down. Okay. And then up to 0.4, you have nothing, right? And then at C, which is at 0.4 distance, you have minus 10 again. And then you come over here, and go back to what? 0. Okay. So this is how the shear force diagram look like. Okay. Then we are going to look at the bending moment diagram. All right, we're going to look at our bending moment diagram. So the bending moment diagram, right? I'm going to focus on the positive side, and I'll tell you why later on. Okay, so this is our bending moment diagram. So this is X, and this is our moment. Okay, so the same 0, 0.15, 0.4, and this is 0.55. Okay, so now if we look at the structure now, okay, if we look at the structure now, okay, so where this structure will fail, right? If we were to look here, where this structure will fail, the structure will fail somewhere between point B and point C. And they did not tell us, hey, they just say, the question just say what? Okay, calculate the determine